Namaskar everyone. Today we will solve some numericals. On our screen, we are seeing a beam which is fixed at left end and simply supported at right end. Length of the beam is 1 meter and this beam is experiencing a load of 1245.87 newtons at a distance of 0.775 meter from right end. Let us try to solve this problem using displacement method. So, while solving it through displacement method, first of all, we will consider this configuration of the beam. In this configuration of the beam, both the ends of the beam have been considered to be fixed. And in this configuration, the reactions are R1, R2, capital M1, and capital M1 bar. For this configuration of beam, we can write second order ordinary differential equation as EI d square V by dx square equal to minus M1 plus R1x minus 1245.87 bracket start x minus 0.25 bracket close. Now integrating throughout, we get equation, and again integrating throughout, we get the equation of elastic curve. Here C1 and C2 are the constants of integration, and from boundary conditions we find that C1 and also C2 would be equal to 0. At x equal to L bar, where L bar is the length of the beam, deflection is 0, and this gives us 0 equal to minus M1 L bar square by 2 plus R1 L bar cube by 6 minus 1245.87 by 6 bracket start 0.75 bracket close raised to power 3. And also at x equal to L bar, slope is also 0, as you can see. So this gives us another equation, equation number 2. Multiplying equation 2 by L bar by 2 throughout, we obtain equation 3. Now, subtracting equation 3 from equation 1, we get another equation from where we can find out the value of R1 as R1 equal to 1051.2028, and considering equilibrium in vertical direction, we get R2 equal to 194.66 Newton. And putting the value of R1 in equation 1, we get M1 equal to 175.2 Newton meter. So we have solved reactions for this configuration. Now let us consider another configuration of the beam in which right end of the beam is experiencing an angular deformation of theta. Here the reactions on left end are capital R3, and bending moment reaction on left end is capital M2, and reaction at the right end is vertical direction capital R4 and bending moment M2 bar. For this configuration of the beam, we can write the deflection equation EI d square V by dx square equal to minus M2 plus R3 into x for a section at a distance x from the left end. Integrating throughout, we get expression of slope, and again if we integrate throughout, we get equation of the elastic curve, where C1 and C2 are again the constants of integration. Now using the boundary conditions, at x equal to 0, V is 0 gives C2 equal to 0, and at x equal to 0, slope is 0 gives C1 equal to 0. Also at x equal to 1, deflection is 0 gives us 0 equal to minus M2 by 2 plus R3 by 6. And at x equal to 1, slope is theta, that gives us EI theta equal to minus M2 plus R3 by 2. Now multiplying 5 by 1 by 2 throughout gives us equation 6, and subtracting 4 from 6. This is equation 4 and this is equation 6. We get the value of R3 as 6 EI theta and R4 equal to minus 6 EI theta and M2 equal to 2 EI theta. Now, evaluation of equation B at x equal to 1 gives moment at right end of beam as minus 4 EI theta, where equation B is this, the equation of bending moment. Now, for moment equilibrium at right end of original beam. Now, here is the original beam. Now, see here, bending moment at the right end is 0. So that means M1 bar plus M2 bar must be equal to 0. So here we have M2 bar plus M1 bar equal to 0. So this gives us expression of theta as 58.4 divided by 4 EI. Also, when we superimpose configuration, this configuration to this configuration, we get the original configuration, right? Now, that means by adding the reactions of the two configurations which we just discussed, we can get the reactions of this original beam. So we can write now R is equal to R1 plus R3, R bar equal to R2 plus R4, M bar equal to M1 plus M2, where R bar and M bar are reactions of the original beam, and R1, R3, R2, R4, M1, M2 are the reactions of the configurations which we just discussed, the two configurations which we just discussed, and these two combinations when superimposed give the original configuration. So from here, the value of R comes out to be 1138.8 Newton, R bar comes out to be 107.1 Newton, and M bar equal to 204.4 Newton meter. Now let us solve this question again using the force method. This is the original configuration. This is statically indeterminate. To solve it through force method, first of all, we will make it determinate by removing the reaction M1. So if reaction M1 is removed, we get this beam, which is simply supported. Here we can see from our equations of statics, R3 equal to 0.75p and R4 equal to 0.25p. Now, let us apply moment M1 on the left hand and let the reactions, vertical reactions, in this case be R5 and R6. And let us now find out the values of M1, R5, and R6. If we apply the reflection equation on this configuration, given in figure 6, we get EI d square V by dx square equal to minus M1 plus R5x. Integrating it throughout, we get the expression of slope. Again, integrating throughout, we get the expression of the elastic curve. And if we apply the boundary conditions at x equal to 0, v equal to 0 gives C2 equal to 0. And at x equal to 1, v equal to 0 gives C1 equal to C1 equal to M1 by 2 minus R5 by 6. And at x equal to 1, d square v by dx square equal to 0 gives R5 equal to M1 and R6 equal to minus M1. Now, using equation 8, slope at left end of the beam in figure 6 is obtained as 1 by EI bracket start M1 by 2 minus R5 by 6 bracket close, where equation 8 is this one. Now let us again consider figure 5. This is the figure 5. Now here, deflection equation for a section at distance x from the left end can be written as ei d square v by dx square equal to r3x minus p bracket start x minus 0.25 bracket close. Integrating throughout gives us the expression of slope. Again integrating it gives us the expression of elastic curve. Now again, we get C2 equal to 0 using the boundary conditions. And using the boundary condition at x equal to 1, v equal to 0, we get 0 equal to r3 by 6 minus p into 0.75 raised to power 3 divided by 6 plus c1. Usage of equation 10 gives slope at left end as, now equation 10 is this, and putting x equal to 0, we get the equation of slope as 1 by ei bracket start p 0.75 raised to power 3 by 6 minus r3 by 6 bracket close. Now, for compatibility of angular displacement at left end of beam, now you see that our original beam is this one. At the left end, the slope is 0, the theta deflection, angular deflection is 0. So for compatibility of angular deflection at left end, angular deflection in this configuration in the left end plus angular deflection in angular, sorry, yeah. For compatibility of angular deflection at the left end, the angular deflection in this configuration plus angular deflection at the left end in this configuration must be equal to 0. So we get this expression 1 by ei bracket start m1 by 2 minus r5 by 6 bracket close plus 1 by ei bracket start p into 0.75 raised to power 3 divided by 6 minus r3 by 6 bracket close equal to 0. And from here we can find out the expression of m1 as 204.4 Newton meter. Reconsidering figure 4, deflection equation at distance x from left hand can be written as, let us look at the figure 4. This is the figure 4, the original beam which we want to solve. So if you consider a section at distance x from the left end, we can write the deflection equation as ei d square v by dx square equal to minus m1 plus r1x minus p bracket start x minus 0.25 bracket close. Now substituting the values of m1, r1 and p1 and evaluating at x equal to 1 gives us value of r1 as 1138.8 Newton and r2 equal to 107.1 Newton, and m1 we have already found out 204.4 Newton meter. Now let us look at this beam. Now here let us try to find out plastic limit load using equilibrium method. In this beam, we know the reactions. At the left end, this beam is experiencing a reaction of moment reaction of 204.4 Newton meter. At the left end, vertical reaction is 1138.8 Newton. At the right end, the vertical reaction is 107.1 Newton. And this beam is experiencing a vertical load of capital P. For this beam at x equal to 0.25 from left end, we can write that the bending moment is equal to 1138.8 divided by 4 minus 204.4, that is 80.3 Newton meter. So for this, now the bending moment diagram would be like this, where at the left end, bending moment is minus 204. At x equal to L by 4, bending moment is 80.3 Newton meter. Here we have joined points D and C. Here it is worth appreciating that triangles ADC is similar to triangle BJC. And therefore, we can write AD by AC equal to BJ by BC. And this gives us BJ equal to 153 Newton meter. And again in figure 8, IB plus BJ becomes 80.3 plus 153, that is 233.3. Now, if you want to express IB plus BJ in terms of load capital P, then IB plus BJ equal to IJ can be written as P divided by 5.34. Now, when load P approaches plastic limit load, bending moment diagram will be like this. Here we can see when load P approaches plastic limit load, bending moment diagram will be like this, where A dash D dash now is the plastic moment MP, and I dash B dash is also equal to MP. Again here, triangles A dash D dash C dash is similar to B dash J dash C dash, and therefore we can write B dash C dash by B dash J dash equal to A dash C dash divided by A dash D dash. And we know from that we can find out MP equal to B dash J dash divided by 0.75, or B dash J dash equal to 0.75 MP. And if we add up I dash B dash and B dash J dash, we get I dash J dash as I dash B dash plus B dash J dash equal to MP plus 0.75 MP equal to 1.75 MP. And we have already found out from equation 12, Ij equal to P by 5.34. And when P is the ultimate plastic limit load, we can write P ultimate by 5.34 equal to 1.75 MP. And that gives us P ultimate, the plastic limit load, equal to 9.3 MP. Now, we know the yield point stress is 250 megapascal. And we can use the bending equation MYP by I equal to sigma YP by Y, where MYP is the yield point moment, I is the second moment of area about the neutral axis, and Y is the distance of the topmost fiber of the beam from the neutral axis. And from here, we can find out MYP equal to 41.66. Shape vector, which is MP by MYP, has been given as 1.2. So therefore, MP becomes 1.2 into MYP equal to 1.2 into 41.66, and that becomes 50 Newton meter. And therefore, usage in equation 14 which is P ultimate equal to 9.3 MP, gives us the plastic limit load P ultimate equal to 9.3 into MP, that is equal to 9.3 into 50, that is equal to 465 Newton. Now let us solve the same problem using principle of virtual work. So the beam under consideration is in front of our screen, is on our screen, and that is this beam is experiencing a load of 1245.87 Newton in the vertical direction at a distance of L by 4 from the left end, where L is 1 meter in this case. So this beam is experiencing a load of 1245.87 Newton at a distance of 0.25 meters from the left end. Now, first of all, we will conceive an admissible collapse mechanism for this beam. The collapse mechanism for this beam is shown in figure 9. Here we have considered two plastic hinges. One hinge is at location A and another hinge is at location D. And we can see here that BD equal to 0.25 theta 1 and that is equal to 0.75 theta 2. And this gives us theta 1 equal to 3 theta 2. Now, here plastic limit load, the P ultimate is acting at point B. So the external virtual work becomes P ultimate into 0.75 theta 2, where 0.75 theta 2 is equal to BD. So, and the internal virtual work is caused by rotating MP through angles theta 1 at point A and by rotating by angle theta 1 plus theta 2 at point D. So internal virtual work becomes MP into 3 theta 2 plus MP bracket start 3 theta 2 plus theta 2 bracket close. That is equal to 7 MP theta 2. Equating external virtual work to total internal virtual work, we get P ultimate into 0.75 theta 2, that is equal to 7 MP into theta 2. So this gives us P ultimate equal to 7 divided by 0.75 into MP, that is equal to 9.33 MP. In the last question, we have already computed MYP, yield point moment equal to 41.66 Newton meter. And shape factor has been given to us as 1.2. So MP now becomes equal to 1.2 into 41.66, that is 50 Newton meter. And the ultimate plastic limit load becomes 9.33 into 50, that is equal to 466 Newton.